Yeah, hello and welcome to the IFT research call. Today, Farooq will present on GossipSub improvements. We gave this talk in a similar format, the libp2p day that was during DEF CON times. And yeah, we have a few more results that Farooq will present. So yeah, Farooq, the stage is yours.
Greetings. I'm Farooq from VAC Deep Research. Uh, mainly, today's topic for talk is GossipSub scaling for large message handling. The need for efficient large message handling in the P2P GossipSub is rising, and previously the focus was on minimizing the network voice message dissemination time. Now, preserving peer bandwidth is equally becoming important for the Ethereum use case as well as for other applications. Let's have a brief overview of the GossipSub. We have a full message mesh where every peer maintains close to D connections. Obviously, the peer tries maintaining the window between D low and D high, where every received message is forwarded to all the peers in the mesh, except the ones from which we received that message. And at the same time, we also maintain a gossip mesh where we just announce the announcements about the received messages in the form of I have announcements after the heartbeat intervals. Okay, this is a general depiction of the full message mesh with degree 3. So any peer relays whatever the message received to its neighbors, and the neighbors then can relay it next to their neighbors other than the ones from which the message was received. Okay, a fair mesh degree is actually sufficient for disseminating this message to the entire network. But in some cases, for example, in the case of network partitions or in the case of adversaries, we also do maintain a gossip mesh or metadata only mesh where we connect to some other peers that are not our full message mesh members, and we simply announced the IDs of received messages to these mesh peers. So with help from the full message mesh and the metadata only mesh, we can assure resilience in the network, and we can assure network-wide message dissemination in a fairly shorter time, because having a larger or a reasonably moderate mesh degree increases the probability for the message to propagate through all possible, or at least through the optimal or some near optimal paths. Okay, and in the cases where the message was not reachable through the mesh, peers can definitely fetch the message using I want messages that was received through this metadata only mesh. Okay, now the peers delivering the messages early to the mesh, definitely they get to have a reward. They get to have a better peer score. Same is the case with I want replies. Peers replying to messages, they get to have a better peer score. And after the heartbeat intervals, we keep on maintaining and improving the quality of our mesh members. Okay, then there are certain performance enhancement measures in GossipSub. For example, we have generally roughly in a network of n peers, we can disseminate the message to the entire network in approximately log-base T of n rounds, assuming that there are no duplicate peers selected in our path to the destination. Obviously, this is an assumption, and there are generally a large number of duplicates there. And in every transmission round, we have roughly this number of transmissions that are carried out. So every next round gets to have more and more peers involved, and we kind of start having a quicker spread to the network. One performance enhancement is the third publish. If the publisher or the peer that introduces the message to the network starts sending to some F number of additional peers in addition to the full message mesh peers, our transmissions per round, they can increase by this number here as well. Okay. Then the I have and I want message combination, they have certain roles to carry out. Number one, in the case of partitions or some non-conforming peers or malicious peers, they assure network-wide reachability of messages, because I have are announced, and anyone needing a message can simply send an I want request to fetch that message. I want messages also reduce message dissemination time because the far off peers on listening to a I have announcement can request for the message and they can get that message quicker than the actual message spread path. Okay. And then obviously there are scoring mechanisms where, like, if I requested for a message through I want, and if someone did not reply me, I probabilistically try finding out or try penalizing the peers who did not respond to my I have request. And then there is another important performance enhancement measure that is recently introduced in GossipSub version 1.2. That is I don't want message. On receiving a very large message, we can announce our remaining mesh peers that I've already received the message and they should not send the same message to us. Okay, and under general arrangements, this combination works fairly fine. But the problem is, as message sizes start to rise, we start seeing significant rise in message dissemination latency, and this rise is actually much higher than the expected rise. Also, there are much higher fluctuations in the message dissemination time, and at the same time, we also see spikes in bandwidth utilization. Uh, Latency rise and bandwidth utilization rise, they both are bad. So our main agenda was to try to minimize the latency as well as the number of messages transmitted in the network. So if we start looking from the very basics, we can say that message sending time to a single peer can be computed as message size over data rate plus the propagation time needed to for that message to reach to the destination, assuming the message can be transmitted in a single go. Okay, that actually means that over 100 Mbps link, a 10 kb message dissemination time can be approximately 100.8 milliseconds, where 100 milliseconds is the latency and zero point 0.8 milliseconds is the message transmit time. But this message transmit time rises from 100.8 milliseconds to 180 milliseconds for a 1 MB message. In case of D peers, we have to make, let's say if D is equal to 8, we have to make 8 announcements. So message dissemination time rises to approximately 740 milliseconds. In practice, we have seen that this tau d of 1 MB actually rises by several hundred milliseconds, mainly due to the congestion avoidance mechanisms maintained by the transport layer. We carried out this one experiment where we transmitted 12 messages into the network, and we sampled the network after every 100 millisecond intervals. We simply probe the peers that have received a copy of the message, and every 100 millisecond, after every 100 millisecond time tick, we count the additional peers that got to receive the message. This is the first transmitted message, and similarly, this one is the last transmitted message. The first column is the overall message dissemination time to the network. You can see the message dissemination time for the first message is much higher than the remaining of the messages. This is mainly due to the to the lower congestion window at the beginning of the message dissemination in the network. Here, these columns are very interesting. These are 100 millisecond samples. Like after every 100 milliseconds, we count the number of peers that receive the message, and we show these messages here. So we can see roughly around after 14 or 1500 milliseconds, first 2 peers got to receive the message. So first full message mesh received the message around after 1500 milliseconds. And usually heartbeat intervals are much lower. In this case, heartbeat interval was 700 milliseconds. So after 700 milliseconds, the sender also announced the I have messages, and many peers also had requested to receive the message through I want requests. And this peer was actually already sending the message to the remaining peers. Interestingly, many of those peers that were sending the I want requests were also already receiving the same message from some other peers, because message reception of this much size generally takes several hundred milliseconds to complete. In this example, we have seen like the first message reception completed in around 1500 milliseconds. Even after the congestion window rises, yes, we get to receive the messages a little early, but even in that case, it took quite some time for the message to got propagated to the mesh members. Okay, so first bigger problem is I want requests that are generated by the peers eagerly to receive the message much early. If we try to see the impact of these I want requests, we have now plotted up to 1.5 0.4 MB message transmission, starting from simply a 50 KB message transmission. We simply transmit 12 messages to the network. We don't compute first two messages. We assume those first two messages that they are just considered for raising the congestion window, and we don't count the I want requests and other things generated by those messages. So the data here reported is for the the next 10 messages. We can see the number of overall I want requests on the right-hand side legend, this bar. This rises massively with the rise in message size. And we can also see up to 160, 155, 160 I want requests were generated by a single pair. Okay. And remember, there were only 10 messages transmitted in the network, because GossipSub 1.1 permits a peer to make multiple I want requests for the same message, because replying to I want requests is not mandatory in 1.1. In 1.0, it was mandatory. So peers make more and more requests. Same is the case with I want replies. We have seen up to more than 120 I want replies by a single peer. And generally, these peers are the early receivers, the receivers that were on the optimal path of the message propagation. They received the message early, they announced the I have messages early to the network, so they got to have a much larger number of I want requests. Eventually, the message dissemination got slower to the full message mesh peers because of this equation, because now those peers had more and more data to transfer to the network. So at least I have combination is no more a performance improvement in my year. We simply disabled I want requests. I know disabling them is bad, but just to see the impact of I want requests, we simply disable them just to see what happens. So we got to see a significant latency improvement in message dissemination just by disabling the I want messages within the network. But we still need to maintain the I want messages and I have messages in the network, because I have messages are the only mechanism of very quickly announcing the message availability to the network. And at the same time, I want messages help us fetching the messages faster in the network. But we need to make some constraints on the number of I want requests that need to be made. And also we need to see some other factors before making an I want request. That is the first take from this point. The another take that we can take from this figure is there is a large store and forward delay involved here between the messages. At every hop, we have 1400, 1500 millisecond of delay involved in sending a very large message. That delay is propagated because libp2p is basically a store and forward kind of router. The peer receiving the message gets to have the entire message, and then that peer relays that message to the next full mesh members. So this store and forward delay actually gets accumulated across the message propagation path. So we need to minimize these I want requests, number one. Number two, we need to minimize on the store and forward delay. So mainly, these are the three things that we need to work on. First and foremost, we worked on store and forward delay. Second one is the overwhelmed peer. Here we can also see the peers doing flood publish and the peers who received the messages early within the network. They were overwhelmed. For flood publish, we had to do some extra work within the network. And for early receivers, we had again to do extra work in the form of responding to the received I want messages. So, and again, there is another aspect that we need to look on, that is the number of, that is the size of the congestion window that we maintain. For example, here we can see the messages. In the earlier messages, they were received a little late by the network peers. And the later on stage, there we have a large number of messages being received within the network very quickly. So this part of the network is a quicker spread part. But here we have relatively a lower spread between the network. And also from message to message, as we proceed with the messages, we start to have this quicker spread early in the network because the congestion window rises up between most of the peers. In case of flood publish and in case of I want replies, generally we are responding to the peers where we don't have very warm TCP connections, so congestion windows are generally low. So in case of doing flood publish for very large messages, generally due to the congestion window, we don't gain much benefits. Okay,
Finish
now
as much as
let's first
possible.
focus. I'm sorry. Now let's
Sorry,
focus on.
that was an accident.
Now let's focus on the student forward delay first. In an effort to reduce the student forward delay, we first looked onto the message fragmentation. We can consider that message dissemination time to the entire network can be simplified to this equation where delta Tx is the message transmission time over all the size of the data we intended to transmit divided by the bandwidth that we had available into the number of hops that had to retransmit that message for that message to reach till the destination plus the propagation time through the path. If we fragment a large message into n number of smaller fragments, any peer, any next hop router can actually get to receive a fragment and start relaying that fragment to its full mesh members while it is receiving the next fragments from its predecessor. So the message dissemination time can be reduced from this path to this equation. So that gives us a significant gain in message dissemination time. Here we have the blue bar shows simple GossipSub operation, and here we have the same message transmitted in the form of 4 fragments, and we could get to see a latency reduction by up to 55%. Okay, and other measure that we can carry out for latency reduction is to use message staggering. Okay, sending to the entire mesh can be completed in this much time, whereas sending to single peer can be completed approximately 1/d of the time that was needed to send the message to the entire network, because we are saturating our entire bandwidth to send data for one peer. Okay, in that case, our spread for first D peers, assuming that data transmission time to one peer was 1 second, after every second, our sending to the other peers in the network actually doubles. And after it reaches to the D number of peers, it actually carries the window of previous D number of peers that received the message. And those peers are now actually spreading the message to the network. It goes relatively faster than this spread. But if we get to see the overall impact of this spread within the network, we did not get to have the expected results. Here, the bar is actually the message dissemination latency for GossipSub. And here, this first bar is the message dissemination time for staggered message sending. Here we realized that sending to one peer has some multiple problems attached to it. Number one, that one peer announces the message availability and it gets to have many I want requests. Number two, if that one peer is also receiving message from many other peers as well, or if that one peer is a slow receiver, basically we get to see that a fast sender is generally blocked by a slow receiver. So basically, due to these two fundamental problems, we get to see much higher latency in this case. But sending to multiple peers, instead of sending to one peer, we can send to a group of 2 peers or maybe to a group of 3 peers. We start to see relatively decline in message dissemination time in the network. Okay. The other thing that we expect to see from message staggering is the I don't want effectiveness. Obviously, if I send a message to one peer, that peer can immediately announce an I don't want message to its neighbors. So those neighbors will not send message to that peer. So we expect a bandwidth reduction in that case, and we noticed a bandwidth reduction from 18 to 45% within the network if we increase the message size from 200 KB to 1 MB. Interestingly, for a smaller message size, we noticed much higher bandwidth preservation. So we experimented it, the same thing, for a 200 KB message size, and we noticed up to 45% bandwidth preservation for all the cases. That 45% is actually received when we send that message to exactly one peer. If we start sending to multiple peers, obviously now the effectiveness of I don't want messages is reduced a little bit, but still we get to preserve, we get to lower the number of messages or the number of duplicates that were transmitted to the network. So the workaround was we fragmented the message. So instead of one message, there were multiple messages traveling in the network at the same time. So the peer doing the staggering could rotate between the messages. We can stagger send message 1 to peer 1, and message 2 to peer 2, and message 3 to peer 3. So at the same time, we have multiple messages, but different fragments propagating in the network. So the overall message dissemination time in the network starts lowering. We combine this thing with I don't want messages as well. So if we now get to see the results, this bar is actually the latency that is claimed by the GossipSub. Now, this first bar is just the message fragmentation. We did not do message staggering. And here are the results for message staggering. This one is we send to one peer at a time. Now we send to two peers at a time. And now we send to three peers at a time. Okay. So next is we further want to investigate on minimizing the number of duplicates in the network and also on minimizing the latency claimed by a message for propagate to the entire network. First of all, it is observed by many findings. For example, in ETH research, also it was observed that for most of the messages, for more than 50% of the messages, the time difference between the first message arrival and the first duplicate arrival was bigger than the end-to-end message transmission time. We also experiment the same thing, but once we try finding out the difference of using I don't want messages here, I don't want messages here, and without I don't want here, we don't see much gain in message dissemination. We hardly see like 25 to 18% bandwidth gain, and that bandwidth gain reduces as the message size increases within the network. We also made one more very interesting observation. This is a simulation where we used variable bandwidth and variable latencies within the network. Like peers were having latencies distributed between 15 to 150 Mbps, and the latencies that were distributed between 40 to 130 milliseconds. Here we have another network where we have same homogeneous setup, like 50 Mbps for all the peers and 100 millisecond latency for all the peers. In this case, because a kind of global sync is established in the network, all the peers get to have the message at the same time, so they get to announce the I don't wants, and once they start getting ready for message transmission, by that time I don't want had been received within the network, so we get to see a much significant decline in network-wide bandwidth utilization. But generally this result, the previous result, seems more realistic because we have variable latencies, variable bandwidths available in the network, so peers get to have the messages within different time. But one thing that we need to investigate is that 50% bandwidth saving is not claimed even in this kind of network. Again, the biggest problem falls in two things. Number one, the peers getting the message early were also getting I want requests from many other peers. And another problem was we are looking on the message reception time, like we are looking on the first message reception time and the time difference of the first duplicate message arrival time. Actually, we should rather look on the message transmission time. The moment a peer started receiving a message, before the message had completed, because message completion consumes like several hundred milliseconds, even more than a second in some cases, as we have seen in one of the previous slides. During that time, all of the mesh members, or many of the mesh members, they also start sending the same message to the network. So we need to have some mechanism for earlier identification that someone else is also trying to send us a message. There we introduce the concept of a message preamble. So whenever a peer intends to send a message to the network, rather than immediately sending the message, that peer can simply first send a message preamble announcing that, okay, now I'm starting to send a message that is going to be maybe 1 MB large. We can make multiple actions for that. For example, we can consider I don't want as a message preamble, but I don't want generally is considered to have some different semantics. So we can say we can introduce one extra RPC message. That is exactly what we did in our next work. But message preamble actually announces the availability of the message to the peers, at least on receiving that message preamble. the receiving peer can at least defer sending I want requests. Now message length becomes very important. The defer interval that can actually be perceived from the message length that was announced between in the message preamble. The second thing that we did was we don't need to send multiple I want requests, at least for large messages. And also for very large messages, we can make it mandatory for a peer to respond to the received I want requests, and we can penalize the peers that are not responding to these I want requests on time. Okay. So if we don't get a message on time, we can always generate an I have message after a defer interval, and that defer interval obviously can be computed from the message length. That is the one thing that we can do. Another thing that can have a very massive impact is once I started receiving a message, other mesh peers, they are not aware that I'm receiving the message. So I need to inform them. One way of informing those peers is that I can again send a new control message saying that, okay, I'm receiving a message that is going to be maybe 1 MB long, and that mesh member can obviously compute the time that is needed for receiving a 1 MB long message. So message preamble along with I'm receiving message can ask my mesh peers to defer sending a large message to me for a reasonable time. And if that time expires and I don't send and I don't want announcement to my mesh peers, obviously they can start sending that message to me at the same time. So considering this mechanism, here is the situation. This bar is the bandwidth claimed by GossipSub, standard operation. Okay. It is the bandwidth that was utilized. Here we have the effect from I'm receiving message alone. Here we just optimize I want announcements and we don't use I'm receiving message. Here is the bar number 3 is the merger of these two approaches. The first two, we are using I'm receiving as well as we are optimizing I want requests. And the last part, it is mainly for the reduced sending. Instead of sending to D peers, we start sending the message to D low number of peers, and we send I have announcement to the remaining peer. So any peer needing a message can send back an I want request to get that message. So here we can see up to 55 or 60% bandwidth reduction for large message transmissions. Okay. Even we notice the same bandwidth reduction for messages starting from 200 or 250 kbs up to 45, 50, 55% of bandwidth reduction. At the same time, latency reduction can only be received if we can manage to minimize or reduce the outgoing message queue sizes at the peers that are on the optimal paths. So we also experimented that, the same test case, the same network. Now we experimented by increasing the message size. Obviously, for smaller messages, we did not see much benefit over latency, but as the message size increases, we start seeing a reasonable gain on latency. Okay. If we further try to increase the traffic in the network, for example, now in this case, we introduce up to 140 messages to the network. We start from 20 messages and we reach up to 140 messages, and we place very short inter-message spacing, like every message introduced exactly after 50 milliseconds of the previous message, just to intentionally build some outgoing message queues. So in that case, we get to see a reasonable fall in network voice message dissemination time. At the same time, we can also see there was not much gain seen in the bandwidth for this I'm receiving and I want optimization, the merged approach. The reason is we are sending very small messages to the network. So we did not get to have much benefit or much gain from these kind of message transmissions. Okay. So what are the next agendas? Generally, currently we can see this is the libp2p specs repo, and right now there are 4 open PRs. This one is introduced by us. We intend to introduce the message preamble and as well as I'm receiving message for large message handling. And at the same time, there are 3 other open PRs, mainly for minimizing bandwidth utilization. For example, this PR mainly focuses on achieving zero duplicates. This PR tries to have a situation where multiple publishers try introducing the same message in the network, so they all can also start sending the I don't want in advance, so they don't get that message. And here we have a topic observation kind of thing where a peer can preserve its bandwidth by observing the messages announced by other peers in the network just by receiving the I haves, and a peer can explicit by using some explicit peering agreement can obviously fetch any needed messages whenever it desires to see that. Okay. Now, looking our work, by combining this approach with this approach only, by the way, gives us up to 1.7, 1.8 duplicates within the network. If we try combining this approach with massive staggering, we feel like we can further reduce these duplicates by a reasonable level. That would be one of the next experiments that will carry out. Okay, that is all from my side. Also, there are some reads that are available for our work that we have carried out. There is a blog post on I don't want messages. There's a blog post on large message handling. Also, some of our work is about to get published. That will be available soon. So, questions, please.
Are there any questions? Yeah, and let me just maybe make a comment and start a discussion. You would like to submit offline? Yeah. So actually, regarding this, you might also want to add to the open PR that we already have in the specifications. So yeah. What I just wanted to say is there is also this idea of using just using item once instead of the I'm receiving, which has like a different set of benefits and disadvantages. It's just more on the, let's say, I don't want to say cosmetic, but it's not really, it doesn't change the approach that Farooq just explained. It would just avoid introducing a new message. Some small details would change, and it would make the implementation simpler. And we thought that this might be easier for the peer-to-peer community to accept. But in the PR that Farooq just showed, the GossipSub v20, they also introduce 2 new messages. So it might make sense to have separate messages after all, because you then separate the semantics of them. So there's a different set of trade-offs. Just wanted to put this out here. And then one more thing to consider generally is that many of these improvements are heavily targeted towards is the Ethereum use case. But yeah, we also have Waku, and we want to improve performance for Waku as well. So let me check. Maybe, Farooq, you can take the question that Lena just posted.
Just let me read it.
Yeah, I will read it. Yeah. So when we look at our protocols and optimizing for high user count, intermediate and concurrent users, how would we determine a happy place for our protocol to perform adequately? Are we able to simulate?
Currently we are
Sorry,
simulating.
indeterminate. I was misreading this. We don't know how many users we have within the protocol. Like we have a high user count, and we do not know how many users we have concurrently.
Generally, what mechanism we use is, for example, here we have one use case where we instead we rather simulated it. For example, here we simulated it by ranging from 2000 to 12,000 years. So yes, we can. The best way for that becomes actually that you simulate for a range that we expect to do. Like we can start from a lower possible thing and the biggest area that we want to simulate. The biggest constraint that we get to have from this kind of simulations is the available machines, because obviously simulating a 1 MB message may be, for you can imagine, maybe 10,000 peers, you have to see 10,000 multiplied by 8 into that MB 1 MB message. So quite a high memory footprint is needed in order to carry out those simulations. But we have already simulated by like up to 12,000, 14,000 peers, and we get to have some results. Yes, bigger ones can be carried out. Hardware constraint is one thing that can be considered, and the network size, I would say, we can define a smaller and upper range, and then we can kind of do the runs for all possible variations that we consider. So we are actually aware of what's happening.
Yeah, maybe adding to this also, we did a few mathematical calculate. I mean, some simple mathematical models at first to just see what we think might be network sizes that GossipSub can support. Because clearly there's some scaling limit to unstructured peer-to-peer networks, which we just might not be able to get beyond. And then we stimulate within these ranges. They also should have, sensible um,
Actually, some quick math
range.
can also be done from here. Some very quick math can also be done from here. Basically, these are the transmission rounds. If we have d number of peers, we can imagine like if my network rises by from 1,000 to maybe 1 million, we can, by putting this 1 billion here, we can find out the number of transmission rounds. So the message gets disseminated to the network. The only problem is the number of rounds increases, and the time for that message to reach the entire network is actually this number of rounds multiplied by your latency. If message is getting transmitted in one transmission round, or as many RTTs are needed. You can, for simplicity sake, consider the latency here just for one round, and just to have some ballpark idea that okay, what is going to happen. The other option is you can increase the workload of the peers. As the network grows, you can also try raising this number. But ideally, obviously, there has to be a limit on this workload. So this multiplied by the delay. Generally, this can give you the idea, and then you can obviously consider what is the latency available to you, the average determinant latency, just to be able to find out, okay, how much time will it take for that message to reach the entire network.
Yeah,
So
then
mainly
so
it's a
we
trade-off.
have we have shadow simulations, and we have runs in our VAC lab, which is using Kubernetes. And I think Alberto wants to say something about the DST tests regarding that.
Actually, it was a question.
Then I misunderstood your hand raising. Yeah, but still, go ahead.
It was a question to Farooq. Thanks for the presentation. I don't still understand the difference between the I am receiving and I don't want, because shouldn't be, I mean, aren't they behaving the same if you send the I don't want at the beginning of when you are starting to receive a message, or I misunderstood something?
I don't want is actually a promise that, or a confirmed saying that, okay, I've received a message. The only flaw of not using I don't want as I'm receiving is maybe someone else is sending me a message, and maybe that malicious peer, not non-conforming peer, can maybe stop sending the message, or maybe something happens and I don't get to receive that message fully. In that case, I'm going to need that message. That is one problem. The other problem is I don't want message is in specs, and that is already being rolled over to Ethereum mainnet also. So the community probably would not want, I feel, would not want to change the semantics because that can delay that rollover also. That is the biggest difference. So I don't want is a confirmed way of saying that, okay, I received the message and I'm receiving is kind of saying that, okay, I most likely I'll get that message, but if I don't send and I don't want to you within that X amount of time, you can always resend that message to me. So I'm receiving says, okay, don't cancel sending to me, just defer sending to me. And I don't want says simply cancel sending to me.
Okay, okay, okay. Thank you very much.
There is also one question from Hegel. Okay, yes, we can split the large message into multiple fragments, and the more number of fragments we have, the more latency saving we get to have. In case of bandwidth, we get to see very similar results. In fact, fragmentation gives you more bandwidth utilization because of those additional headers that are involved in the network. Number one, also, just to discuss, fragmentation has certain downsides as well. For example, it allows that opportunity of exploitation for some non-conforming peers. For example, I may never relay last fragment of a message. And since other peers are also relaying that message within the network, so everyone will have some unfinished downloads in their receive windows, in their receiving buffers, and those buffers might get overwhelmed after some time if a large group of peers start doing these kind of acts. Number one. Number two, the message, if full message is not valid, and I'm sending fragments of the message, every receiver can relay that fragment to the next peers. It can only be validated once it's received in the form of all fragments by the receiver. So maybe a false message can also get propagated, or maybe a spam can be introduced to the network in the form of fragmentation. So these are two exploitations that are possible with fragmentation. So that can be considered.
Maybe, yeah, just adding to this, because I think Leonard might have meant, splitting the message in a header and a body, like not this fragment. I'm not sure, but I will just put it out there too. So like the splitting into a header and a body. So in a sense, yeah, Leonard.
Yeah. So I'm coming. First of all, can you hear me? Okay.
Yes.
Okay. So when we were working on the Laos protocol, IOG, and just a bit of background, we got the concept of kind of ranking blocks and input blocks where you had the headers and you broadcast those so that you sent the critical information first and you got that broadcasting going, and then when you had lesser traffic you sent the smaller blocks and ultimately got confirmations. Now it's not dissimilar, because our problem is we're trying to get to optimize for sending messages, and I like the idea of the I want versus I have. I'm just trying to work out how do we get it. We've lots of data which is superfluous to lots of users, but because it's decentralized, we're having to broadcast via your mesh. I'm thinking, first of all, smaller messages, we all agree, I think are optimal, and transmission rounds. So I'm just trying to work, is there a happy place we can simulate that allows us to slice that big message, which could be, for all intents and purposes, could be a message, could be a video message, it could be even preferences, and they're totally unimportant to a lot of people, but because we're decentralized, we have to broadcast to everybody. So I just wanted to say, well, we can slice it up into pieces. I think you said yes, and then the question is, how important is it that all the pieces arrive? Well, it's important to that one person who wants to persist preferences. Other than that, it's not important. So maybe we look at the concept of how do we mark those blocks so that if I'm not interested in it, I kind of don't care about it anyway. So I'm just, that's my questioning. But by the way, great presentation as well, Farooq. And I'll probably reach out to you because we're trying to work out if you have a situation where you're packaging a protocol and you might be handing it to an end user. You really want to know what the limits of it are, and that's why I'll ask the questions. Thank you.
Thank you. One thing that comes to mind is if you can spread the header within the network, and every receiver knows the IDs of the messages that it will be needing. There can be two options. You can use IWants to fetch the exactly wanted IDs. And other much quicker mechanism can be the unwanted IDs. You can simply send I don't want for that. So your mesh operation that continues in the similar mechanism, and the ones for which the I don't want was not transmitted, they can be eagerly pushed through the mesh.
Yeah, interesting. It's like having a sense protocol. Yeah, I think there's more distance to travel on this. I'd like to take it offline with you as well. Thank you.
Sure.
And then regarding, like telling that somebody's not interested in specific parts, this would be more like a layer above GossipSub. Like GossipSub would be agnostic to that, but Waku could, do that on top of GossipSub. Yeah, are there any further questions? Let me I will link the PR here just for everybody's reference. And Alberto, like your question regarding the, I don't want and I'm receiving, they're semantically different, but you could convey this information in the I don't want to. And I wrote a comment in this PR to explain this. This might be exactly what you thought. It's like my comment on the bottom. It's just a different way to do exactly, to kind of get to exactly the same improvement, but it has its own disadvantages. So it is ultimately just preference thing. Yeah. Are there any other questions? So yeah, in this case, then let me thank you, Farooq. Thanks again for this great talk. Yep, we had this discussion already at libp2p day, which was very very helpful. Got to talk to CCs from other projects about that too. We also have a discussion in the forum about that. So yeah, please join. And in the because we have the Christmas and New Year break, we will not have a call in the next weeks, but the next call, let me actually check in the calendar, it will be on 15th of January will be the next slots. You will be able to, you can find this in the IFT research call schedule maintained by Philip, and you can also always ask in the Logos Discord's IFT research call channel. Yeah, thank you very much, and see you next year. Thank you.
Thank you.
Thank you very much.